want to talk about a cell and particularly an interesting circuit where I could get second order behavior. In fact, a very designable second order behavior. But basically, in this case, I'm actually only using one op amp and I'm using two capacitors but no inductors. A lot of times there's an assumption I need to have inductors to get second order behavior along with a resistor and capacitor, but it's not necessarily the case. And this is one interesting example of such a circuit. In this case, a circuit with two capacitors and three resistors, and you can just kind of see what kind of dynamics come out of this. Now the core thing to notice in this circuit is look at this R and C right here around the op amp. This is really the core of the circuit. Because really what you're realizing is this is an integrator. And in fact, you could look at the response and from V1 to V out, or V out to V1, is related to that time constant R2 and C1. And that kind of gives you kind of the starting points. We're building around an integrator topology. We see this around a lot of different circuits that are built to give you second and higher order structures purely with R's and C's. Start with an integrator, see what happens. And then what we end up doing is having a resistor coming into an intermediate node V1, a second capacitor, and an R here. So it's like I've got another RC circuit, but I've got this interesting feedback from the output into this middle node. Well, certainly I could write KCL at that node, which would give me this particular expression. And then with a couple layers of math, I can kind of group all the V1 terms together, get the V in and V out term. From knowing I have V1, I know I have V1 is related to the integration structure, plug that in, and then bring V out to the other side and just start grouping things. And it does get a little bit messy, and what you end up seeing when you go through this is that you end up getting a pretty reasonable response. Again, still +1 at the far end. This is always what you want to aim for, is elements with the S squared, elements with the S, and then 1. And then a term over here for V in, which kind of gives you what the gain term of this is going to look like. So as a result, I can then say, well, my tau squared is this combination of capacitors and resistors. My gain is going to be R3 over R1. And then I get a resulting response. I can try to solve for tau over Q, which gives me a relatively messy expression for Q. But it is still usable. And you might think, well, okay, this is kind of messy. But if, again, I needed only one op amp, needed two capacitors and a bunch of resistors, and I can get a whole range of Qs out of this by heavily choosing different ratios of capacitors, and the resistors also have some effect in the circuit. You can see this in different ways where I could do this, where the capacitors could be like the messy part and the resistors could shift. There's a whole range of kinds of ideas, but it gives you one idea. This is a very classic cell known as a Rauch biquadratic cell. And is a very interesting sort of topology how you can solve for this. And if I sort of plug in some values for 1 megohm for 3 of the resistors, and the C's are 1 picofarad and 9 picofarad, I get a sense where my time constant is 3 microseconds. Again, notice sort of the C1 and C2, so they sort of multiply together in a square root, so it gives me the 3 out of that. The gain is -1 because R1 and R3 are the same. And then Q turns out, because of the choice of C's and R's, as a Q of 1. I could imagine getting a bigger Q by changing these numbers. I could imagine getting a lower Q by changing these numbers. But it gives me a pretty interesting structure and circuit that I can then start to implement and build sort of second order structures. And for those who've had to work with structures, particularly discrete circuits or on-chip circuits where you have inductors, they get very difficult and messy, and it's very hard to get the values you often want. And so this is one interesting way to get around some of those